We're going to shift gears a little bit now. We're actually going to bring on the first set of presenters onto the stage that are actually going to share some of their research papers. And so I'd like to invite Brett Gordon, who is currently a professor at Columbia Business School, but who will in a couple of weeks be joining the faculty of Kellogg's to be a marketing professor there, along with Jerome Shimizu, who's the chief research officer of Insight Express. And they'll be presenting their findings on the rise of big data and the fall of significance. Brett, Michael. Jerome.
Okay. So thank you for joining me today. So we're going to talk about a little bit of a story. And the story might sound like it starts as a bad bar joke. But I hope it'll end with a useful point of learning for you all. Jerome and I met while we were on a flight from, I guess, San Francisco to New York, and had a bit of a chance to talk about our respective areas of work. And during the course of those 5 long hours, we found out that we did have some points of interest in common, and the outcome of that was the following. And if your first thought is, well, I'm really happy I wasn't sitting next to you, you probably wouldn't be alone. But the way that we came about this discussion was we were talking about how the world had kind of changed with big data, the advent of big data. And that historically, one of those things that have changed is the fact that a lot of the samples that you deal with when you're analyzing some kind of test, let's say, a lot of those samples used to be very small relative to the population of interest. And that's changed now with a lot of big data type sources of information. So we wanted to introduce to you, or perhaps reintroduce to maybe some of you, a concept called the finite population correction factor. And we'll make clear what that is in a little bit. But the basic point to kind of take away is really a rule of thumb, and that is if you're looking at some kind of sample, and that sample is small, say, large, say over 5% in terms of size relative to the population that you're studying, you may need to use something called the FPC to adjust the way that you learn about your data, the way that you conduct tests, such as hypothesis tests, the way you calculate margins of error, the way that you calculate p-values. And to make that point a little bit more clear, I want to give you the intuition before I'm going to give it to Jerome for some concrete business examples. But to give you the intuition, let's consider pandas. Okay? So suppose we want to know the average height of the world's panda population. Now, you might have heard that there aren't that many pandas in the world today. So let's say that there's about 1,000 pandas in the world. Okay? And suppose magically that I'm able to obtain a sample of 999 of those pandas. Okay? Now, this is obviously a very large sample relative to the population. And if I measured the average height of all those pandas, suppose I get the average to be about 50 inches, plus or minus a margin of error of 5 inches. Okay? Now remember, I was trying to calculate the average height of the population of pandas, and I succeeded in measuring all their heights save for one. So the question is that margin of error correct? Am I really that uncertain about what that average panda height truly is? Because you can see that if I just could measure that last panda's height, I would know with certainty the average height of the panda population. The margin of error would be 0. And that's the problem. The problem is that the usual ways you calculate a margin of error, a hypothesis test, a p-value, etc., don't often take into account the fact that if the sample is very large relative to the population, the numbers are going to be off. And that's what the FPC then tries to fix. Now, this is an extreme example I've shown you here, and my guess is that most of you aren't interested in the heights of pandas. So I'm going to pass it off now to Jerome, who's going to talk about 3 illustrative examples of the FPC in a more of a business context. So.
Okay, great. All right, thanks, Brett. So yeah, so really the premise of this paper was to bring to attention that for big data, we need to be using big data statistics. And many of these things, they've been around for a while, but they're essentially new for the practitioners in this space. So as Brett said, we're going to go through 3 illustrative examples of before and after applying the finite population correction factor. So the first example we were able to demonstrate this on was for sales data. So this data set is probably the oldest big data set that we've used in the industry space for things like ROI analysis, for doing things like test versus control comparisons of what was the lift for a particular marketing element. And in this case, we're able to get data from our friends at IRI and Polk. And we're looking at one of the most basic metrics of significance or of statistics that we look at, and that's statistical significance. So you can see in these examples, in both examples, we see pretty dramatic improvements in statistical significance, going from what would be normally considered not significant to being highly significant results. And again, this is the exact same data set where we're applying this new adjustment factor. So a second example of big data and applying the finite population correction factor is cookie level data. So think of what's behind a lot of the web analytics platforms in the marketplace. Again, we see a really massive improvement in statistical significance going from not significant or directional, as we sometimes say in the industry, to highly significant. And the third and final example that we looked at was behavioral data. So again, think about the kind of data sets that are underlying these attribution models. This is a more recent big data set. In this case, we're looking at another very commonly used KPI, another common metric in the industry, that's confidence intervals. And in this case, you can see going from traditional statistics of an infinite size universe, infinite size population to a finite population, pretty massive improvements in having more precision of accuracy and measurement. So just to summarize, what did we learn here? Well, most importantly, we learned that big data allows the data nerds in your organizations to now benefit from these big data statistics. Remember the 5% rule that Brett took you through, that if you have at least 5% of the population that you're sampling, then you should be thinking about this adjustment factor. And by the way, I just want to mention there's a much more longer paper that we put on the ARF webpage, so check that out. There's 2 other additional rules of thumb that you should check out with that. The other summary point I wanted to mention here is that this adjustment factor has broad applications. In the tests that we did some basic comparisons, things like chi-squared tests and t-tests, but this affects even more advanced modeling. So if you think of econometric modeling, attribution modeling, ANCOVA modeling, marketing mix, all of those things are affected by this new way of thinking. And then I wanted to close with just this final comment, is this is just one example of revisiting one of the basic assumptions of statistics, this size of the universe question. And there are plenty of other things that you could take a look at in light of big data. For example, the shape of the population distribution and seeing what happens when you're able to leverage big data. Thanks. One final comment I would say is that, again, if you want to know the end of the bar joke from Brett of what happens when a data scientist and economist walk into a bar, you can find out later today. We'll be around at the drinks reception. So thanks, guys. All right.